the number of milliseconds until ignition. We plot the time-temperature relationship on a graph, and from this we can get the apparent activation energy necessary for ignition. What I'm trying to do with this apparatus is to prove or disprove part of Boden's arguments on the hotspot theory of explosive ignition.
If Lieutenant Truesdell succeeds in this project, it may be fairly important. I'm Professor Sinclair of the Material Science and Chemistry Department, and I've been following his progress with great interest. He and I have regular conferences to discuss this progress. While it's very much Mr. Truesdell's project, I'm heavily involved also. What pleases me most is that regardless of the end result, the work that has been done has been good.
Cybernetics, ops analysis, plasma physics, resource management. Today's words, tomorrow's world. In Monterey, California, the Naval Postgraduate School helps prepare officers of the United States Navy for tomorrow's naval world by providing them with a graduate education of the highest academic caliber. The mission of the postgraduate school is to provide advanced education for commissioned officers and to give them the kind of academic background which is in increasing demand in a navy of mushrooming technology. The school is recognized and accredited by collegiate accrediting organizations and offers bachelor's, master's, and doctor's degrees in a variety of scientific, engineering, technical, and management fields, covering electronics, ordnance, oceanography, chemistry, meteorology, mathematics, physics, computer systems, and operations analysis. Original research is conducted in all of these fields in order to maintain academic excellence, to attract and maintain a strong faculty, and as a means of offering students stimulating and motivating educational opportunities. For officers with only basic science courses in their undergraduate education, there is a special engineering sciences program designed to bring them up to speed in the exact sciences of the master's degree programs. The school offers about 30 different curricular choices in technical and management areas and administers about 30 others at civilian universities. These programs are designed to infuse a higher level of technological education in the general line, to prepare officers for technical specialization or subspecialization, and to provide officers of the Staff Corps with advanced education in their fields. A majority of the courses are in the basic scientific and engineering disciplines. Heavy emphasis is placed on mathematics, oceanography, chemistry, and the physical sciences generally. Because of the Navy's special requirement for broad technical competence, most curricula at the Naval Postgraduate School offer unusual breadth in options and electives in subject areas related to the student's major field. Approximately 90% of graduates remain in the unrestricted line. Under the subspecialist concept, the unrestricted line officer, whether aviation, submarine, or surface type, pursues a normal career pattern afloat and ashore after completion of the school with utilization in his subspecialty area.
I'm Professor Williams, head of the Central Computing Facility. Computers play a very important role in the student's life here. All students and more than half of the faculty use the computer significantly in their research work. This is our major configuration, a 316 Model 67, consisting of 2 central processing units, of which this is one, accessing a variety of storage devices, including core, drum, disk, and tape units. The school acquired its first computer in 1954. This present installation is among the most advanced in educational institutions in this country today. The primary mission of our central facility is to provide effective computer support for all classwork and research at the Naval Postgraduate School. The user writes his program in one of a number of available languages, has it punched on cards, and then submits this deck to the operators for processing. The results are presented in a variety of forms. Normally, he would ask for printed output. Sometimes he'll want a graphical representation on our plotters, or possibly a dynamic display on a cathode ray tube. Here, Captain Skeeto is working on research on bounding surfaces with applications in ship and airplane design.
Using this device, we can investigate various elementary surfaces and adjoining surfaces meeting boundary conditions of position, slope, and higher order derivatives. We can change the shape, rotate it, zoom it, to examine any point, and translate it. This device allows almost immediate interaction with the computer and performs tasks in seconds, which for normal calculations would take weeks, months, perhaps.
Such capability offers tremendous potential to the engineer of the future.
Maybe in order to satisfy intuition a little better, we ought to get a little closer to the real world. And
the management curriculum gives the student with little technical background advanced education in scientific methods of management, so that he can keep pace with the Navy's rapidly expanding requirements in management systems. Courses include such subjects as organizational theory and administration, management economics, quantitative methods, management psychology, logistics, and business and government.
I'm Dr. Borsting, the chairman of the Operations Analysis Department. What we have been doing here today is discussing a typical operations analysis problem in sonar detection. What we're doing is educating Navy line officers, Coast Guard, Marine, Supply Corps officers, and Army officers in the graduate work in operations research and systems analysis. One of the basic things we're stressing is an analytic approach to decision making at both the fleet and Pentagon level. The Navy, like most large organizations, is emphasizing systems analysis techniques to aid the decision maker. One teaching technique we find very effective is gaming and simulation.
Well, those were the numbers that I pointed out before, that we've got $2,000 operating cost for both offensive systems A and B. That's a total cost on offensive systems. And we're committed to $3,000 operating cost for defensive system B.
Are we reasonably well agreed then that we'll buy 15 units of offensive B?
I think so.
And that leaves us $150 for intelligence. For intelligence. We'll buy $100 worth of offensive intelligence and $50 in defensive intelligence.
Well, I think maybe we ought to just put all of our emphasis on the
15 seconds is all.
Well, let's go ahead and buy
Decisions ready
defensive
now.
intelligence then. Are you agreed?
I think so.
$150 of defensive intelligence.
Not we lose it anyhow.
Right.
Okay, that's it. Unfortunately for the umpire, probably good for you, war did occur in the last period, and I'll have to go out and compare your results with the results of the other team, and I'll be back in approximately 5 minutes and let you know what happened.
Fine.
Well, we certainly would have been a little bit better off if we'd had the war in the next period and we had our offense up.
It's apparent that we're short in Defense A, taking such a beating in the last war. So if we shift into, or put our R&D funds into Defense A, I think that's the place we should put them and leave our offense alone.
You build up Defense A then?
Absolutely.
That's right.
Do we have to support a second?
No, we're all ready to procure everything we need in there. So really, we have $3,150 that we can either...
Gaming and simulation, such as the example you have just witnessed, provides one effective way for students to utilize the basic concepts of probability, economics, OR methodology, and other subjects, which forms the core of the operations, research, systems analysis curriculum.
10 units? 10 units?
The The technological breakthroughs in meteorology and the ocean sciences since the end of World War II have been staggering, and we're still just getting underway. We're reaching farther and farther up into the sky with satellite meteorology, and going deeper and deeper into the sea for our oceanographic studies.
Travel along the grain longitudinally with the boring shell up forward, cutting a perfectly cylindrical hole. Extending out into the water are the siphons that pull water into the water. My own area is marine biology, which involves studies that seem pretty mundane to some people, but they're very important to anyone connected with ships and ocean engineering. Sound, but leaves it practically hollow. I have two pieces of wood here that show the fact that it looks fairly sound externally, but internally the wood has been totally chipped away, as is shown here in this one with the top removed. We're studying the fouling and boring organisms that attack various types of hulls and wharves. It's a very complicated job identifying some of these destructive organisms. I'd say that perhaps 1 or 2 students out of every 40 in the oceanography program will take his master's in biological oceanography. This is a piece of redwood that was under the wharf for a few weeks at a depth of about 20 feet. This is a perfect area for this kind of research. Not only does it have a wide variety of organisms inshore, but there is deep water canyon in Monterey Bay, which is full of many deep sea specimens. This is our biological oceanography beach laboratory, where we have running water in aquaria and can keep living organisms that are collected out in the sea alive. I'm Dr. Hatterley, and this is Lieutenant Commander Flower, one of my students, who is currently studying one of the panels that was brought up out of the bay this morning and making an analysis of the boring and fouling organisms that have collected on it.
The first thing to do with this problem is to identify the organisms that we find on the panel. This is a very difficult task in that these organisms live very close together, in fact, on top of each other many times. It's only through this organized research that we're able to determine what will affect them and be able to combat the problem we have of fouling organisms on our ship's hulls.
That canyon I mentioned before is right out there in Monterey Bay. It goes down to a depth of from 6,000 to 9,000 feet and stretches out to sea for about 40 miles before it joins the ocean floor. Roughly speaking, it has about the same contours as the Grand Canyon of the Colorado. I keep telling my students that if we could only drain the bay, we would have a major tourist attraction. Not that this place doesn't already have tourist attractions. For me, one of the peripheral joys of being at the postgraduate school is that I keep saying to myself, surely this must be one of the most beautiful places in the world. You know, Robert Louis Stevenson lived here and wrote about this place. He said, everywhere, even in the quiet weather, the low, haunting presence, the thrilling roar of the Pacific hangs over the coast and the adjacent country like smoke over the battle. something about this place that is good for the human soul.
No matter how good the facilities and the academic program are at a school, it's really the faculty that determine the excellence of the program. Here at the Naval Postgraduate School, we feel that we have an outstanding faculty equal to the best of our engineering schools in this country. As a matter of fact, this is confirmed quite frequently by our departmental visiting committees who come from many of these schools. For example, the requirements for a master's degree throughout the country vary from school to school. Some only require attendance in class. Here at the Naval Postgraduate School, we do insist on a thesis and original research, making this probably one of the most demanding and one of the most complete master's programs in the country. There is quite a tradition behind the Naval Postgraduate School going back to the 19th century. And if we take it that far, back to the days of these sailing ships, our officer trainees received their instruction aboard ship, and they're berthed amidships. For this reason, they're known as midshipmen. And after they finished their course, they'd move aft and join the wardroom officers in the afterguard. But with the advent of steam, it became impossible to continue this aboard ship, and this led to the founding of our Naval Academy in 1845. But beyond this, as time went on, with the increase of steam widely throughout the fleet and the introduction of electricity and sophisticated ordnance, even the Naval Academy wasn't satisfactory for the advanced education needed. For example, if officers were going to design ships, and they were, they'd require advanced education in ship design. Our first graduate students went to the Royal Naval College in London and to other universities in Europe. By the turn of the century, MIT had come into its own, and we were sending students there. Then, in 1909, the Naval Postgraduate School was established on the grounds of the Naval Academy at Annapolis, and it's been growing ever since. By the end of World War II, though, the facilities even there were inadequate, and the school was relocated here to Monterey in 1951. With the technological revolution that is taking place, the program at the Naval Postgraduate School is becoming deeper and more comprehensive every year.
Today, our faculty includes a broad spectrum of recognized scholars in science and engineering.
As delta S approaches 0. And then getting the sum vector signal plus noise.
In the liberal arts, efforts are divided between government and the humanities.
Hitler then was probably right in his estimate of the situation. That is to say, through 1940, he was probably right that the Germans should have attacked the Soviet Union when they actually did. Now, having decided by late 1940 that he was going to attack the Soviet Union, Hitler having decided this, let us now look into some of the implications of this thing. This is going to be war on a giant...
Many of our faculty have published textbooks or the results of their own original research. Approximately 3/4 of our civilian teaching faculty are PhDs, and the proportion is increasing. We're very proud that both in the classroom and the laboratory, we have absolutely top-flight men.
This experiment differs a little bit from the more usual type of experimental research in that it represents a sharp break from the previous work that we've been doing. In a sense, it's a long shot. We expect it to work and hope it'll work well, but we have quite a bit to do yet before reaching that goal. If it does succeed, we hope it'll represent a small breakthrough and allow us to explore an unexplored region. I'm Dr. Crittenden of the Physics Department, and this is Lieutenant Wardle, and this work represents part of his activities in connection with his PhD program. I think Lieutenant Wardle should explain the details to you.
We're attempting to generate intense pulses of very high frequency sound, first at 500 megahertz and later at 5 gigahertz or 5,000 megacycles per second. Such sound, of course, is too high in frequency to be heard by the ear, but it's still sound in that it's an elastic vibration in a material. We're using a giant pulse laser, this portion of the apparatus. The output of the laser is split in two halves, and the two halves are then Doppler shifted by a spinning rotor in this evacuated chamber. The Doppler shifted beams are then fed by mirrors focus through this lens down into the sapphire cube down here, where the nonlinear reaction of the sapphire to the very intense light can be expected to produce sound at the beat frequency between the two light beams. Professor Crittenden conceived this experiment, and we've worked together about a year and a half to design and construct the apparatus. We think we're now to a point where we can expect the predicted theoretical performance very soon. We're now charging the capacitor bank in preparation for firing the laser. Ready to charge?
Right.
Charging. Stand by to fire.
Okay.
3, 2, 1, fire.
Kind of sound powers we'd like to get and are planning for are about 100 million times the present available sound at this frequency range, which is in the vicinity of 5 kilomegacycles or 5 gigahertz. With that sort of power level, there are a number of phenomena that should show up that have never been seen before.
I'm Dr. Vavra from the Aeronautics Department. The students come over here to the Turbo Propulsion Laboratory after they have been working with paper and pencil for a long time. Over here, they are faced with reality. They are making tests with actual machines, and they're asked to compare phenomena which they measure with theoretical results. We may start them out on fairly simple test equipment. This is a cascade test rig, where we can have a visual look at the flow patterns of the fluid particles passing through a blade of a turbine. And then we put them to work on more complicated problems. These students are making a detailed investigation of a turbine wheel which I helped design for NASA. This $100,000 rotor is for the upper stage of the so-called Nova rocket, a real monster. Of course, this rocket is for space explorations after we reach the moon. This upper stage is driven by liquid hydrogen and liquid oxygen, and will develop 1.5 million pound thrust, large enough to put this whole lab into orbit.
Lieutenant Beck will explain what we're doing in this portion of the laboratory.
There are no theoretical means by which the stress distribution in a turbine wheel with a complex shape such as this can be determined. With our hot spin test rig, we are able to measure these stresses at operating conditions in excess of 1800 degrees Fahrenheit and at speeds of 50,000 RPM. These stresses are transmitted electrically through high-speed test rings up over to our control panel where they are recorded. During this operation, the pit is evacuated to a pressure of 500 microns.
You see, we are working on the problems of the future, and there is no end in sight. We take part in the technological revolution, and we plan to stay right with it.
The Navy of tomorrow is a technological Navy. The number of assignments requiring postgraduate education is on the rise day by day. The naval officer who combines operational experience with a graduate education is more valuable to the Navy and to himself. The officer interested in a postgraduate education can get detailed information from current Bureau of Naval Personnel instructions on the subject, and can indicate his desire for postgraduate education simply by listing it on his officer data card. Selection for the postgraduate school is on the basis of demonstrated professional potential and past academic performance. About half of the officers who enter the postgraduate school each year are surface or submarine types, and the other half are aviators. Postgraduate education, whether in engineering or in management, is here to stay. In these days of rapidly expanding military technology, graduate education is a vital adjunct to operational experience. The Navy must keep pace. If the Navy is to remain a key arm in national defense and a ready instrument of national policy, it will need the best educated minds that America can provide. It will need them. It's going to get them.